So I was thinking, what should I speak here? Something related to the spectral theory, and decided to tell you or discuss with you one particular case, particular result from our joint work with Benjamin Audoux and Enea Parini. So they are both from Aix-Marseille University. All right. Let us start with something very preliminary. So throughout the talk, we will denote by B, well, where, so the, right, so the open, say, unit ball in Rn. And let us first consider the standard eigenvalue problem for the Dirichlet operator in the ball, so everything is simple. And okay, so in this case, we can just separate the variables, right, and distinguish the radial component, the angular one. So the angular component gives rise to the spherical harmonics, which impacts in the multiplicity of eigenvalues. And in particular, it's very well known that the second eigenvalue has the multiplicity exactly n. So lambda 1, lambda 2, sorry, equals lambda 3, etc., equals lambda n plus 1. So geometrically, this can be explained because in the following way. So we know how the second eigenfunction looks like. So it is all the time positive in the half ball, negative in the opposite half ball, and 0 in the equatorial cross-section. And since we can rotate this eigenfunction, basically there are n linearly independent positions for this 0 set. Basically, when the 0 set coincides with the orthogonal coordinate hyperplane. There are n such coordinate hyperplanes, so multiplicity is n. And well, this chain of equalities is something which we would like to obtain for the p-Laplacian. So now we come to our nonlinear settings. So let us consider this eigenvalue problem number 1, which is a nonlinear eigenvalue problem. On the left-hand side, we have this classical p-Laplacian, which is this divergence of this gradient in the power, and p is greater than 1. So, of course, problem number 1 is written in a pointwise way, but we have to understand it in the weak sense. So just this is the formal way of writing that. When we work with the p-Laplacian, the problems start from the very beginning, from just the ground level. Problems about the spectrum. For instance, it is a major open problem whether the spectrum is discrete. It is unknown up to now, or whether maybe whether it contains the whole semi-axis or not. So this is absolutely unknown. Nevertheless, something can be said. In particular, we can construct the sequence of so-called variational eigenvalues of that problem, say by means of the following minimax variational principle. Yeah? So here, what do? We maximize the Rayleigh quotient over the set A and minimize this maximum over all admissible sets A. So under the admissible set here, we mean the following. So this is just subset of the Sobolev space, which is symmetric. Well, under symmetry, we mean that like element belongs to A if and only if minus element belongs to A. So symmetry in this way. Well, closed. Well, you can ask even compact if you want. And what is essential is that this function gamma A has to be greater or equal than K. K is the index of the eigenvalue. So what is gamma A? It is the so-called Krasnoselsky genus of the set. And it is, well, an example of so-called index of the set. And it is defined in the following way. So suppose that we can map our set A in the continuous odd way into the sphere, like Euclidean sphere of dimension k minus 1. So suppose we can find maybe several such spheres of different dimensions, And well, so the Krasnoselsky genus of the set A is the minimal dimension of the spheres for which there exists a continuous odd map from this set to the sphere. Well, this is the main object for us because we will work with this today. Great. So, well, although we don't know a lot of things about the spectrum, some things we know, for instance, that this set is good because the first variational eigenvalue, let me write it here, the first variational eigenvalue is the actual first eigenvalue of the p-Laplacian. And the second variational eigenvalue is the actual...
Restriction, actually. I can't understand. Some example probably you can give some example.
Well, examples will be later, actually. So we will construct some sets. You mean the construction of Krasnoselsky examples of the set? Okay, we will see it. Yeah, certainly. Right. Okay, so I just want to say that below this lambda 1 there are no eigenvalues, and in between lambda 1 and lambda 2 there are no eigenvalues of the p-Laplacian. Also, by construction, well, by properties of the genus, and can be shown that this sequence of variational eigenvalues increases, so and tends to infinity. That's fine. That's fine. And we want to prove, let me recall that we want to prove the chain of equalities. It's our main aim, although it's unachieved. And the main abstraction in the obtaining this chain of equalities is the following fact. Well, basically it follows from the definition of the eigenvalue. So, say for instance, to obtain this chain of inequalities, we have to bound lambda n plus 1 from above by lambda 2. Then it will close up the chain of inequalities and transfer it to equalities. To this end, we have to find a symmetric closed set A with Krasnoselsky genus greater or equal than n plus 1, and simultaneously the maximum of the Rayleigh quotient has to be less or equal than lambda 2. Well, it's trivial, but the point is that it's not hard to find a set satisfying all these properties, but it's hard to find a set which simultaneously have a good upper bound. Okay, yes. And if we, for instance, can find such set, then by definition, lambda n plus 1 is less or equal than this maximum, and less or equal than lambda 2, and we are done. Well, and let me say now the following thing, which will follow actually from the information on the next slide, that if we know that the eigenfunction, second eigenfunction of the p-Laplacian in the ball has the same nodal structure as the second eigenfunction for the linear Laplacian, then we really can obtain this chain of equalities star. Without this knowledge, and this is an open question, so there is no information about that, in fact. So we cannot obtain at the moment the chain of equalities, but we have something which is slightly weaker. And let me present its result. So first, although we don't know how the second eigenfunction looks like, let us artificially construct a good eigenfunction, symmetric one, which is positive in the half ball, negative in another half ball, and 0 on the equatorial cross-section. So we can do it artificially. And the corresponding eigenvalue will be denoted by, by this symbol.
What does it mean, make it artificially?
Okay, so...
Does it mean that we minimize only over the set of functions?
Yeah, exactly. So, in fact, we have a, say, ball. We just split it into two half balls. And let us find the first eigenfunction here. And symmetrically reflect it here with a negative sign. Well, and that's it. So basically, then lambda with this symbol equals to the lambda 1 of the p-Laplacian over, say, well, half ball. What is, how to say half ball? I don't know. Like that. So if it is a half ball. So this is the artificial construction, but it can be done. It's quite easy. Yeah, later on we will call this lambda, like lambda O minus, just because this subindex is written in the LaTeX, like lambda, like O minus. So to define it somehow. Okay, so and this symmetric, like good symmetric eigenfunction will be denoted here by phi later on. So it is quite easy to show that lambda 2 is less or equal than lambda O minus. So whether it is equal actually less, strictly smaller, it's unknown, but we can obtain the following result. That not only the second eigenvalue is bounded from above by lambda O minus, but the whole chain of inequalities up to lambda n plus 1 is bounded from above by lambda O minus. Well, like among experts, let me say that I think nobody will doubt that there has to be an equality. So, because it has to be like that. Say, like, looks like it It's a good candidate to the second eigenfunction. But we don't have a methods to prove that fact.
Well, but I don't understand. For any n?
Well, basically we fix p, any p, we fix any dimension greater or equal.
N is a dimension, yeah?
Capital N is a dimension, right. So, and it is a dimension, and it is in the index.
Oh, so you have an eigenfunction
Right.
with associated vector,
Mm-hmm.
and then what n here? Any n?
No.
It's a dimension.
So actually, n is the dimension of the ball. It is the dimension of the ball.
I see.
Right.
I see.
Yeah, this is like that. Well, so the proof is actually quite elegant, not hard, but I never seen like similar constructions in the literature. That's why I think it's nice. So, okay, so we know that our function is sign changing, so plus and minus, and let us split it as like phi. This is the symmetric eigenfunction, by the way. So split it as phi plus minus phi minus. Great. Okay, let us now define the set B, which consists of all possible rotations of this function phi. And just to make it like formal, let us parameterize it by the subindex x, where x is the element of the sphere, and well, where phi x stands for the rotation of our given function phi in such a way that, well, let me just show you the picture. It will be simpler. So we have a sphere. We pick any point on the sphere, let's like point x, right? And we have a vector x. And let us rotate our function phi in such a way that its zero set is orthogonal to the vector x. And for the definiteness, let us assume that vector x points in the direction of the positive part of phi, just for definiteness. Well, that's good. And now this parameterization allows us to define the function f from the set B to the sphere as follows. So we just map phi of x to the x. Simple, yeah? And this is, of course, an odd homomorphism. Why it is odd? Because, okay, we had a, say, positive part here, negative part here. We choose a minus vector, and now we have a, say, negative part upside down. So that's why the function is odd, essentially. Which implies, by the definition of Krasnoselski genus, that this genus has to be less or equal than n. And now, like, okay, believe me at the moment that the Borsuk-Ulam theorem easily shows us that the index cannot be lower than n. So it is exactly n. And therefore, just by definition, we can bound this lambda n from above by the maximum of the Rayleigh quotient over the set B, which is exactly lambda O minus, because the p-Laplacian is also the isotropic operator. So no rotations doesn't affect the value of the Rayleigh quotient. Great. But let me recall that we wanted to go one index up. So we wanted to obtain this, actually, this inequality with n plus 1. And to this purpose, let us upgrade the previous construction. So let us consider not only rotations of our given function phi, but also the rescalings of its positive and negative components. Rescalings means like we multiply it by functions, by numbers a and b, where a and b, just to keep the LP norm of any function from a, let us assume that they belong to the LP sphere. So these are the numbers, coefficients. So of course, if it is a subset of the Sobolev space, if we choose alpha equals beta equals 1, then we restore the previous set B. It's just pure rotations of our eigenfunction, which, okay, basically it means that the B is a subset of A, nothing else. And by the properties of genus, this implies that genus of A has to be greater or equal than genus of B, which is n. And our aim now is to show that these rescalings help to actually increase the genus to 1. Namely, our aim is to show that the genus is greater or equal than n+1. plus 1. If it is so, then we are done. Well, suppose by contradiction that the genus is exactly n. In particular, by definition, there exists an odd map from A to the sphere of that dimension. And okay, so the geometric idea of the things which will be written on the next slide is basically the fact that this set A, it looks like a Klein bottle in the Sobolev space. So this set A is something like a Klein bottle in the Sobolev space, and we want to show that this Klein bottle cannot be mapped in the odd way to the sphere. Let us consider now a map from this product of the sphere times the interval to the set A, which is defined in the following way. So here functions, well, we have basically rotations, and the rescaling factors depend on the variable t. Yes, and these guys belong to the sphere. And we choose them in such a way that if t equals 0, then they are equal to 1 minus 1, while at the value t equals 1, this pair is equal 1, 1. Why do we do that? Because, okay, by definition, if we take t equals 0, then we basically have h equals this phi x plus minus phi x minus, which is just fx. It is just a function. And we know that the map is, well, odd. It's again, because we have positive negative part, we reverse them, and we have a minus sign here. So the function is odd on the 0 level, zero layer. Okay, on the other hand, if t equals 1, then we have phi x plus phi x minus, which is the absolute value of function phi of x. So we have two positive bumps, we rotate them like that, and the function becomes the same after the rotation. So, which means that the function is even if t equals 1. Great. So let me recall that we defined the map H from sphere to A. And on the previous slide, we assumed that there exists a map, odd map from A to the sphere, which is map F. Therefore, the composition acts from this direct product to the sphere, right? At the same time, if t equals 0, then we have just maps from the sphere of the same dimensions, which is odd, while if g equals 1, if t equals 1, then we have a map from the spheres, from sphere to the sphere of the same dimension, and this map is even. That's great. And now, basically, the idea is to show that for the continuous mappings, when the G is a continuous mapping, so this is impossible. The switch from odd to even, such switching is impossible. And this can be provided, well, using the notion of, say, the degree of the mappings from the spheres. And there is a Borsuk-Ulam theorem, which is Borsuk theorem, which says that any odd map has an odd degree, while any even map has an even degree. And what is the last component is that this degree is preserved under the homotopy, under the continuous change. And of course, like, these guys are homotopically connected with each other, so they must have the same degree, but this is impossible. So this is a contradiction. And what? So finally, okay, we have proved that the index, genus is greater or equal than n plus 1, which means that lambda n plus 1 does not exceed this maximum of the Rayleigh quotient. And it's not too hard to show, it's quite easy task to show that this maximum is actually, the value of the Rayleigh quotient is just a constant over all set A. And this constant is lambda O minus. So we restore the complete chain of inequalities. So let me say probably just a couple of words before the next slide is that, so the first thing is that up to my knowledge, there are just no results available about the actual multiplicity of variational eigenvalues in the nonlinear case. So that just for any domain, like in dimension greater or equal than 2, whatever. So there are no example of the case where, say, lambda k equals lambda k plus 1, up to my knowledge. This is something which is very, very close to this multiplicity case. And interestingly enough, so the proof, of course, works in the case p equals to 2, and it provides the full chain of equalities. And it doesn't have any reference to the spherical harmonics. So it's a kind of independent argument which has some Klein-Bottle in its structure. So perhaps there is some connection with maybe I don't know, maybe with spherical harmonics and these Klein-Bottles, but we are not clever enough to say more right now. And okay, maybe as a very last fact, just some additional information which is quite nice. Let me say the following. In the paper by Benedict, Drabik, and Gierk, it was proved that, well, lambda 2 is bounded from above by lambda O minus, which is fine, but what is important, it was proved that lambda O minus is strictly smaller than lambda, which is the second radial eigenvalue, let me call it like that, in the case n equals to 2. And in fact, like many years ago, Alexander Ilyich advertised me that paper, and perhaps it was the moment when I started to be interested in that subject, actually. So thank you for that. Great, so it was obtained by some combination of analytic and computer-assisted arguments. So that's a quite interesting result. But in any case, using our theorem, we can embed here one additional term, which is actually like a lambda 2 less or equal lambda 3, which is less or equal to lambda O minus, which is smaller than lambda O, okay, second radial eigenvalue, sorry. So which means that any third eigenfunction of the disk is non-radial. So what we can say is that it is non-radial. If we know that it has this structure, then everything is fine and we're happy. But unfortunately, up to now, only this restricted information is obtained.